Hi, I'm Rob Knapp. I'm from Wolfram Research, and I will be talking about geometry and meshes, which is sort of our geometry project that sort of unifies typical mesh computations with symbolic computation. Styles you can use that actually can be quite efficient. In fact, using certain techniques, you can get essentially the same efficiency as you would get with like a dedicated C program, though you have some advantages. Not quite as fast, but the development time is so much smaller that it's much more efficient. And I think a really good example of using some of the techniques that I'll go through very briefly today is that the finite element, most of the finite element code that Oliver showed in the previous talk was written in the Wolfram language. And there's a few bits that are specialized, that were bottlenecks, but most of it is written, and it's actually done using automatic compilation of some of the examples I'll show you today. So now I'm really bad with these mouse pads, so you may have to forgive me. Okay, I might need a little sysadmin help here. Oh, so it's the left. Yeah, okay, got it. Sorry. See, I'm hopeless. Okay. So this is a first example, and the idea is when you're thinking about doing numerical computation with Mathematica or the Wolfram language, it's really often good to think in terms of bigger things. And I'm going to have a really hard time with this mouse pad, but we'll try. In fact, oh man. Okay, so I'm just going to enter all this stuff at once because it's going to be a bit hopeless. Okay, so what I've done is I've taken a really big data set. And so my goal in this is to find, the idea is I've got a big set of random numbers, okay, which just happen to be uniformly distributed. They might not. And my idea is I want to find the largest difference between any two consecutive numbers. Okay, so I'm not sorting it just as they were spit out by the random number generator. So basically one way to do it, and this is the way you do it if you're used to Fortran or C, or something, you'd write a for loop, and this looks almost exactly like C. So I take the part of this, the part of the data, I look if the max is bigger than my current one, then I update the maximum, and so on and so forth, and that takes 5 seconds. Now, if I think differently and say, OK, well, I want to find the biggest difference, so why don't I first take the differences and then look for the maximum of that? OK, and that's what this code does. And actually, this is more expressive in terms of what I'm trying to do anyway. I mean, it's probably easier to read. So I take the differences of my data, which takes consecutive differences, if you look at the documentation. Then I take the max, the absolute values of those, and I get my thing. And it's nearly 50 times faster to do it that way. And I think so I think the lesson is, if you can think instead of doing little bits of your computation, you can think of doing, OK, can I work on a big chunk of data with 1 or 2 functions? You're going to always be faster. And we've written a lot of functions so that they do sort of the inner stuff really fast and efficiently. And then, I mean, these are not sophisticated functions. Differences, max, abs, those are simple functions, but still using them is very effective. And so, but if I do that, I can do this. I can actually do 1,000 samples of that, and I can get kind of a rough histogram of what the distribution looks like. Whereas if I'd done it with that 5-second one, we'd still be waiting until the end of my talk. So that's one quick example. OK, so wow, this thing is rough. Oops, I went the wrong way. OK, so let's look at one of the key things to doing stuff efficiently in Mathematica. And that is this attribute called listable. And a lot of functions have this attribute. And basically if something is listable, it means we call it threading over lists. But basically, it does things element-wise. So this is going to first do the multiplication. So it's going to multiply 1 by 3 and 2 by 4. And then it's going to add 5 and 6 to it. And you can extend to. And the advantage of using these operations in Mathematica is Mathematica, if all that list is the same type, then Mathematica can do optimized operations. For example, if these were really big lists of machine real numbers, Mathematica would actually do the arithmetic in some of the functions it actually just automatically does in parallel threads. So you're getting some sort of sub-kernel parallelization there just for free, just by doing it on big operations. I mean, there's thresholds which are much bigger than size 2 before we try to parallelize, but that's the idea. Okay, so the listable, the efficiency here is potentially enormous. So let's make a test thing. Let's evaluate the sine function. Okay, that takes no time at all. And then let's try and evaluate doing map over the sine. Okay, so this is two ways of doing the different thing. And as you see, sine is probably internally parallelized a little bit. I mean, my machine has well, I have no idea what this machine actually has, but my machine has 4 cores, so you can get quite a speed up. And map, actually, this is much more efficient than doing it in plain Mathematica, kind of like that first for loop, because this is another, so your function may be too complicated to do in a single thing like this. Okay, but what map does is it actually automatically tries to compile the function, and if we compile it, it uses, and this is actually using the Mathematica compiler, but there's a little overhead time in doing the compilation. That's pretty small. And then it's just not as streamlined as the plain function. So when you can do a big thing at once, do it. If not, map or sometimes table can be efficient ways to do it because those are auto-compiled. Okay, so let's get up here. Sorry for being so awkward with this. Okay, so other ways you can use listability. There's a couple. I can do this. And I'm going to get this started because this takes a while. And then I'll talk about the other option. And this gives, as you see, sorry for struggling. Okay, so this one takes a long time. So you can actually give the function the listable attribute so that it will do that automatically. And there's 2 ways you can give a function the listable attribute. One is you can use a definition with patterns, which are the down values for the function, okay, and then that'll list over it. Or you can actually define an explicit function. Now the advantage of this is that the upper thing is it's much more flexible. But the advantage of this one is because the function is there and everything's explicit in it, we actually auto-compile this case as well. We can't really auto-compile that, though there's potential in the future we'll be able to do that. And we're working on the technology. But this is auto-compile, and you can see it makes a big difference in the amount of speed for doing the same thing. So often, if you can do things that way, that's quite effective. OK, so on to the next. OK, so another way to do it is you can actually and this I think is a really powerful feature. You can compile a function, and this is using our compile. Now, a lot of things are auto-compiled, so you don't necessarily need to compile everything. But if you have a thing in your code that you know is going to be run a lot of times, it's often worth compiling it, okay, using our compile command. And it's pretty flexible. It has a limited number of native types, but within those sets of types, you can do a lot of different operations in Mathematica. And so I get even more speed out of doing it this way. And the runtime attributes goes to listable says that this is effectively going to act like a listable function. So on the arguments, it'll list over the arguments. So it actually applies. So we're actually applying the compiled function on each individual thing there. So that's a really effective way to do it. And I'll be showing in a bit. You can actually compile using compile. For a lot of cases, you can compile the C code, and you get even more efficiency that way. So as an example of that, I'll show. So here's a fun example. So, and this is something I do a lot, and actually this is kind of what we do. This is showing you a little bit what we do in our internal functions, though we do it in a different way, in a more robust way. So what I'm doing is I'm writing a function here called iterator compile, and I give it a function, and I'm asking it to be an explicit function in this case, the first case, and some options, okay, and it's going to assume that function takes 2 parameters, so it's going to be a map function like R and X, and what I'm kind of thinking of as a logistic map. So it'll compile that, and then it'll run through and 0 iterations to sort of let transients die out, and then it'll look at what it puts the rest of the iterations into bins, so you can see where the function values tend to go. And so see this, you can give it any function that it should map the intervals to a self, or you're going to have it blow up, but that's something you can give any function to. So let's see if let's try it with a logistic map. Okay, so there's logistic. Okay, that worked. And then we can actually do a plot of this. Oops. Oh, I didn't get that properly evaluated, did I? Okay, let's try this again. Okay, and that's what this bin. This happens to be a value where it's sort of done the period doubling and the bifurcations and stuff. And so you can't, if I chose a value with a smaller r, which I don't have time to do, you can actually see. So here's a function that actually puts that together, and it makes a bifurcation diagram out of that. And I think these actually look pretty nice. Oh, no. Oh, boy, oh, boy. OK, well, OK, so I wanted to show you how I can compile this to C to make it faster. Now, this computer apparently doesn't have a C compiler, which seems to me like a horrible sin, but OK, whatever. But yeah, it can't find it. It may well have a C compiler, but but in any case, and if you don't have one in your system, you get this. You can actually install a Visual Studio Express for free, so it's not so hard to do. But it actually makes a nice, I'm not going to show you the whole thing, but it makes a nice looking bifurcation diagram. And even with this, without the C, it did it, pretty interactive speed. And with the C, it's even faster. So that's kind of that example, and it's worth seeing how that works. OK, I still have a little time. So there's sort of two parts of my lesson today. One is that by thinking about big things and compiling things, and even compiling things to C, and even in cases where you can't quite figure out how to get Mathematica to do it, we have a thing called library function that allows you to write a little module in C that might do the critical part of your computation, and that connects directly in with the compiler. So now I'm going to say, OK, so sometimes you want to compile, and then the other half of the story is, well, sometimes you don't. OK, and the point is that if you're doing a particular calculation, like I was doing here, say a bifurcation diagram, it's great. You're just working with numbers, not doing. But here, Mathematica has a lot of functions that work with functions, and by Mathematica have the symbolic form, it's able to do so much more than a typical numerical system. So let's take this example, OK? And I think this is a really nice picture a former colleague put together. So Mathematica, when we give this to say, we're going to compute this integral numerically, when we give it to Mathematica, it sees it very clearly. It actually sees the whole structure, symbolically the problem. It can do some symbolic analysis and decide, OK, this is the right method to use here. This has discontinuity, so I'll break the discontinuity points. Whereas the typical numerical method, it's all fuzzy. All you can do is sample. OK, so I'm going to go. In the interest of time, let's see, I need to go down here. OK, and I'll just show you, I think this is kind of interesting. So what I'm doing here, and this is another thing you can do with the compiler that's not a default. So here I've said runtime options evaluate symbolically goes to false. And so sometimes you want a compiled function as sort of an object. Well, the default is it'll try and evaluate symbolically, which is not, in this case, so useful. So here I can actually give it a symbolic x, and it leaves it unevaluated until x is numerical, which is that's a little known but very convenient option of our compiler, which I kind of wanted to show. OK, now let's do the integral with this. OK, and so I'm getting all sorts of messages. It's done a bunch of bisections, and all these recursive bisections are done right near the discontinuity points, and also because that integral is extremely oscillatory, so it's not getting the convergence it expects. And so just remember that took 0.7 seconds. OK, now let's go up, and actually, if you look at the notebook later, I have some analysis of how you can actually see where Mathematica actually sampled the function. And I'm going to skip that in the interest of time. So let's look at how Mathematica does this. Okay, so Mathematica recognizes the discontinuity, so it breaks it up into 3 piecewise functions, an integral just sums, so it does 3 separate integrals, really. Okay, and then it can sort of, it does an approximation of this, and it uses special rules for oscillatory functions that get a very good approximation very quickly. Okay, so it's actually using the symbolic form to do something here, and let's do this integral again. Okay, now the first time took 0.72 seconds. That's not quite fair, because if we do it again, we get 0.04 seconds. The reason that first time took 0.72 seconds is, well, Mathematica has to load the packages which do the symbolic analysis. So the first time you do an integral like that, it might be slow, but the next time it's going to be super fast. And this is a lot faster than the other version. And it turns out, I won't show you, but if you look at the Computation notebook, this is accurate to 10 to the minus 14th, and the other error has example about 0.0001. So 10 to the minus 4th. So it's 8 orders of magnitude better, done faster. And that's what the symbolic analysis can do for us. Oh gosh, I'm actually doing better than I thought. So I'm going to go through some of the symbolic analyses we do. And then I have one final example if there's time. So some of the this is not an exhaustive list, but this is a fairly a representative list of the sort of things we do. So one that's really important is, like in ND-solve, we identify sparse structure for evaluation, and that's key for actually, say, so when we say compute a Jacobian numerically as opposed to analytically, by using the sparse structure, you're able to use far, far fewer evaluations, and that can be huge in some problems, okay? And so we use that. Also, just doing the sparse linear algebra is much faster, and that's absolutely essential to like this finite element stuff. That we often, we've sort of integrated sparse structure computed from symbolic formula and sparse structure from what we just know the assembled matrix is like in finite elements. So it's all sort of all integrated. We're able to do index reduction for differential algebraic equations automatically. Okay, so if you have a higher index problem, we can try and analyze that and figure out what the real index is, do index reduction, and solve the reduced system. So it's without a higher index solver, we're able to get fairly efficient solutions. I mean, another good example is discretization of PDEs. So Oliver showed you these PDEs we can discretize, and when we get to the nonlinear stuff, being able to analyze the PDE for the right structure, it's going to be essential to have the symbolic stuff there. Again, another thing we do is heuristic identification of methods based on, and I think that integrate example was good. We chose, for part of it, it was slowly varying, so we just chose an ordinary method. For part of it was quickly varying, so we chose an oscillatory method. Detection of discontinuities. We do that in ND-solve and integrate, a bunch of other functions. And again, we can often simplify the problem by transformations. So those are just some of the really important ones, but there are quite a few. Okay, so I'm being told I'm getting close to the time. So let me just show you this example. I think it's another representative example, which I think makes a really nice picture. And we'll just finish with this picture. If I can get the thing to move. Oh, man. There we go. There. Okay. So this is a neat. I think this is a fun example. Okay. So I've got I didn't show the DE very quickly, but I'll kind of explain what's happening here. Is the DE actually had two different discontinuity surfaces. One is on the surface of this ball, and the other is on this plane. And so what happens is, ND-solve, I just gave it as equations. Actually, the discontinuities appear as the sine function in there. So ND-solve starts from its initial condition and integrates along until it hits that first discontinuity. Now, those discontinuities I chose so that actually the vector field points inward towards the ball on either side. If you try that with an ordinary method, what's going to happen is it's going to choke. It's going to say, which side do I go on? I can't go on either side. I'm stuck. And sometimes they'll oscillate and chatter, and sometimes they'll just get stuck. In this case, it actually just gets stuck in 3D. But ND-solve computes the discontinuity. It basically sums the vector fields to use a so-called sliding mode solution. It does that. Then it hits another discontinuity. And this one actually slides on the interface between the plane. And as you see farther up, it escapes from the ball and continues on the plane. And that's something without the symbolic analysis, unless you wrote the particular tool to it, you'd never get the solution to. And so I think let's end with that example, and we can go to questions.